What we're looking at now is test 12, guys. Okay? And it's going to be sections 9.1, 9.2, and 9.3. Even though there's only 3 sections, there's a lot of material. Okay? It's not going to be a full test though, just 75 points. Okay, not a full test. I said around, I didn't know. I didn't make it. Yeah, that was my estimate. So after I made it, 50 points was too few. There's too much topics or too much stuff to be covered for it to be a 50-point test. Okay, so it's 75 points. It's still not a full test. And there's only 3 sections, but we did a lot in those 3 sections, a real lot. And we talked about a lot. There was a ton of conceptual and a good amount of math at the same time. So this is a quite lengthy test that you're going to be looking at as far as material is concerned. This is the last topic, obviously, for your final exam. So let's go over some general stuff first, conceptual. We did a good amount of math the other day. You guys were to watch the beginning of that video last night, and then at the end we'll do maybe another math problem. Okay, but I really want to go over the conceptual stuff. Because last test, most people struggled with the conceptual and the last math problem. The one with the energy levels. We did that in class, we did it in class, guys. I was like so disappointed. So for those of you that had trouble on that, you need to go ahead, thank you, Jeff, and look at the solution at least. Okay, on Moodle, look at the solution. Because we did that same problem in class, I just changed 2 numbers. Anyhow, the conceptual was the concern last test, so I want to start and look at that in depth. First, we need to know, and I'm just giving you ideas here. You need to know what a fluid means. Who can tell us what does a fluid mean? Close, that's a liquid, Max, that's a liquid. No, that's a gas. You just described a liquid and a gas, which are both fluids, but what is a fluid first? What is a fluid? What do we have for fluid, people? Jeff?
Flowing state of matter.
Okay, so something that can flow, that's it. A flowing state of matter. Anything that can flow. That's why solids are not fluids, but liquids and gases are both fluids. The air conditioner is flowing in air, or you're flowing in whatever the coolant is, and it's cooling us as a gas. The liquid at a water fountain flows out of the spout. Now, as Max said a minute ago, though, a liquid takes the shape of its container, whereas a gas does not. Is that clear? A liquid takes the shape of the container it's in, a gas doesn't. And what we're going to see is that liquids have a definite volume. We did this example in class. If you take a 16-ounce cup of water, and I was telling you if you pour it into like a cake pan, it's still 16 ounces of water, it's just a different shape, that's all. Okay? Whereas a gas does not have a definite volume. It has a certain volume, but then that volume will change. It'll expand to fill the room or to go out after that. Okay? You okay? I don't know what's in your hand. You keep looking at it. Okay. Any questions on the definition of a fluid? Okay, and the difference between a liquid and a gas? That's part of flowing, yeah. Okay, so when something flows, the molecules can move alongside one another or pass by each other. All right. We talked about floating versus sinking. Give me some statements about floating versus sinking. Jeff, floating versus sinking. Go ahead.
If it is sinking, then
Again?
if it is sinking, the density of the object is greater than the density of the substance or the fluid.
Good. What about the forces when it's sinking?
If it's sinking, then that means it's F net equals FB minus FG.
Good. And which is bigger, buoyancy or gravity?
The FG, the gravity, is
Good.
bigger, but it's negative.
Very good. These are the 2 keys we have to write down for something that is sunk. Sure, the object is denser than the fluid, but also gravity is outbalancing the buoyant force. Okay? And remember, our general equation is what Jeff said.
And then
Okay?
also, if it's floated, then it's
Go ahead, keep going, Jeff. Go ahead.
FG equals FG. And in most cases, you'll have to sub out FG for mg, which also can be density of object.
We'll get to that. Hold off. But what about the density of the object part first?
If it's floating, then it's just equal. The density of, or no, sorry, the density is less than the density of
Okay? Less than if it's floating. So those are the general statements we should know. And these are just simple inequalities and equations that replace, paragraphs worth of words. If the density of the object is greater than the density of the fluid, then it sinks. All that from one simple inequality. So this is when you study the way you want to write it.
G is force of gravity.
No, wait, this is force of gravity. No, wait. Okay. All right. What else? What else? Okay, we talked about type of flow. I'm just going random topic by random topic. It's not in order right now. We talked about types of flow. What are the two types of flow we can have of a fluid? The two types.
Sorry, I forgot to use some of that shit still. Laminar.
And
So like smooth.
laminar is smooth, streamlined, and what's the other one? Turbulent flow, unpredictable. Remember the analogy, the simple analogy, I don't think I went over it here, but here's what I think about. Do you remember rational numbers are numbers that can be written as fractions or decimals that are predictable, whereas irrational are numbers like pi or square root of 2, where the decimals have no pattern. So what I think about is this. I associate laminar flow to rational numbers. It's predictable. And then I associate turbulent flow to irrational numbers. Its behavior of its decimals are not predictable. Okay? So those are the two things I think about there. But anyway, back to the answer, as Olivier said, laminar is smooth, steady flow. Turbulent is unpredictable, has currents. You see these little like vortexes afterward. Okay? Any questions on those two? What number did we use to generalize? What did we call it? We didn't actually go through it, but it was abbreviated like this.
Reynolds.
Good, the Reynolds number. And if the Reynolds number is really high, what kind of flow is it?
It's smooth. Opposite.
Opposite, Jeff. Look at, if you want to help, ready? Look at this. Remember, this was the formula we used. It was density, velocity, diameter over viscosity. If the velocity goes up, it's moving faster. It's going to be turbulent. So as this number goes up in general, it's more turbulent.
So the less viscosity it has, right?
Yeah, and that was the other thing you said. Objects that are turbulent flow have less viscosity. They're like water and oil. Whereas stuff like, now more like water, not oil, more like water. But things like syrup are going to flow slowly, aren't they? They have a high viscosity, and they, in the end, if you have a high denominator, you have a low Reynolds number. So low Reynolds number is laminar, high Reynolds number is turbulent. Stop, Paul. Stop. Mash.
Wait, what is that number again?
Reynolds number, it's called. We didn't go over the values at all. Just in general. In general. The higher the Reynolds number, the closer it is to becoming turbulent. Okay? There is a break-off point, but I didn't even go into it because it involves a little bit more math than we did. So just the idea, though, the concept.
Wait, the higher is the more turbulent.
Say again?
The higher is what happens?
The higher the Reynolds number, the more turbulent or the closer to being turbulent it is. Now, Reynolds numbers that are extremely high have traditionally turbulent flow, but there are other parameters that affect it as well. If I were to draw a diagram now, here's a cup, okay? Here's water. Here's a layer of oil sitting on the top of the water. And then we have a piece of, say, plastic that has sunk to the bottom. So we have plastic, the density of plastic, the density of oil, and the density of water. What statement could you make relating those three, relating all three of those, Jack Healy?
That the density of the plastic is higher than the density of oil and water.
Okay, but which is, give me more. That's true so far, but what about the oil and the water? Which is more there?
The oil is more dense than the water.
Oil's floating.
Oh, okay, less dense, sorry.
Okay, that's what you would say. The density of the plastic is greater than the density of water because it's sinking. But the density of water is greater than the density of oil because the oil is floating on top. Okay? So it's like a compound inequality. Remember these?
But you could just write that like.
In words, you could write that.
Separately too.
Sure, you could say this and this. It's an and inequality. Compound inequality.
But that's not floating though, because I would with Jack. I would assume the oil is not floating.
Floating, and the oil is floating, absolutely. That's why the oil has the least density,
Oh, yeah.
right?
Actually, I meant the opposite, sorry.
Thanks anyway, Justin.
Whatever.
Oil, whenever you put oil in like water, you'll see a layer at the top floating, and that is floating.
But that's for another reason. It's for the
It's their densities that are causing them really not to mix.
Oh.
I mean, other things cause the molecules not to bond and actually become a homogeneous solution. They're heterogeneous. So they're separate, but because they're heterogeneous, they're going to separate by density levels. Okay? If an object is fully submerged, what statement can you make about volumes in this problem? An object is completely submerged, what volume statement can be made?
Volume is set. Volume is
Stop, man, stop.
volume is inversely related to the density.
Okay.
So that means the density is lower. If the volume is greater, then the density is lower.
Okay, that's good, but your statement is absolutely correct, but not answering the question.
Okay, but that means that the volume is total submerged. So then you could say that the volume is the total, is equal to the total displacement.
Yes, there it is, okay? When an object is submerged, the volume of the fluid displaced is the volume of the object. This was a key that we have to use to answer a lot of mathematical problems. If an object is submerged, VO and VF are the same. Remember, what is VF? It's the amount of fluid that has been pushed aside. If the object is sitting on the top of the surface, it's only pushed aside a little bit of fluid, right? So VF has got to be less than the object. But when the object is completely submerged, they're equivalent. Okay, so submerged, or sinking, I guess, versus floating.
Yeah, you can say sinking too.
Yeah, we could add these to our categories from earlier if we wanted to. But submerged, the fluid is equal to the actual object. In a floating object or a floating situation, the fluid amount that's displaced is less than the actual volume of the object. And the easy way to think about that is to think about, and I know this is, you're not taking baths because you're adults really. Some people take baths, so whatever. You take a bath, okay, and as soon as you put like a foot in the bathtub, when you put a foot in the bathtub, the water level rises a little bit. But if you completely went into the bathtub, it rises even more. So as more of their body or more of the object is submerged, more VF, more volume of fluid displaced. And that was one of the things Archimedes did discover, yes. Okay? Any questions on this so far? Not bad so far, right? This kind of stuff? Pretty reasonable?
Can you draw an FBD about that?
About what?
What you just said? Possible.
It's not an FBD. There's no forces involved.
Another FBD.
You could draw an FBD of any diagram, but that's not about this at all.
You could do Archimedes where you have an object.
Listen, you could draw an FBD for anything, but an FBD will not describe the situation we're talking about. It's a force diagram. This is talking about volume and displaced. I could draw a diagram. Okay, sure, but not an FBD. All right. So a diagram for this would look like the following. If you had some sort of a container and the normal water level was here, and you suddenly put an object in it, and the object floated a little bit, what would happen would be this. The water level would go up, but not that much. It would only go up a little bit. So say this was like 7 centimeters in height. This might be 8 centimeters.
A little tube feeding into a cup.
It's raising up.
You just gave the analogy of the bathtub.
Yeah. That's all I was saying. If it completely was submerged, Jack, if this was completely submerged, the water level would go up even further.
Yes.
Okay? So that's what we're talking about. As it's completely submerged, the amount of fluid that's displaced is equal to the object's volume.
Okay.
When it's floating, only part of it is. So the volume of the fluid displaced is not equal to the object, it's less than the object. Okay? Less than. Alright, you need to know your relationship from the continuity. The continuity equation says, gotta go. Good, Jeff. What does V stand for? Somebody else. What does V stand for here, Paul?
Velocity.
Good. Not volume. Volume is used in other formulas. This is a lowercase v, and you'll see that. If you look online at your formula sheet, you'll see that it's been updated. You should do that. Okay, it's the same formula sheet you're going to get on your final, because we're done. So that formula sheet that you're seeing for this test, it's one page fully, with all the constants at the bottom, they'll all be listed. Okay? Now, what does this tell me? Who can describe what this means? Give me a statement or some conclusion we can make based on the continuity equation for flowing fluid. Paul.
The area of the product of the area and the velocity of the first object.
The first location,
First location
because we're in a pipe.
is the same as the area and the velocity of the second
Oh, I know.
region.
Good, good. What else? What else? Jack.
Well, the area is different, isn't it?
The area is different.
But the velocity is the same.
What is area increases, velocity decreases?
There it is. There it is. Good, Paul. You covered it up
Vice
yourself.
versa.
As the area increases, the velocity decreases, and vice versa. Use the garden hose as the example. You put your thumb over the end of a garden hose, what happens to the velocity? It goes up a lot. So the less area, when you cover with your thumb, less area, more velocity. Velocity and area are inversely related. Okay, inversely related. All right. How about this part? What about the volumetric flow rate, the amount of fluid that comes out in a given time period? If I change the area, if I take my thumb and put it over the area, am I changing the amount of water that comes out in a given time period?
Yeah, they do that. They're all over time.
Okay.
So I don't remember, but it's V times A over T.
From the equation of the day we had, it was like AV times capital V over T, yes.
That's volumetric rate.
Volumetric, that's volume. V over T is volumetric flow rate.
Yeah.
But hold on, because you're making a mistake in your statement. The first part was right.
It would be the same.
It would be the same. Here's what's happening. Listen carefully. Because a lot of you are going to make this mistake. I'm telling you now. It's a misconception. When you move your thumb over the area, okay, less water will come out because there's less area, right? But the velocity went up. So it's actually the same amount of water that comes out in the same time period.
So when your thumb,
So
when
if
your
you-
thumb's off, the water's still coming out.
It's still coming out. Less water is, but it's coming out faster.
Yeah.
Okay? So watch, ready? You're in your backyard, and you want to fill up a bucket of water. And you fill it up with the hose. People think, let me use my thumb over it, it'll make the water come out faster. It doesn't. It comes out with a higher velocity, but the volume comes out in the same time period.
We say higher velocity does not increase the speed for the time.
Higher velocity does not increase the volumetric flow rate at all,
Which is time.
because the area is less, which is a rate of time. Yeah, it's a volume per unit time.
Oh, I don't really understand how you say when there's less area, there's less pressure.
And we're going to get into that. Hold on. That's Bernoulli's principle. Give me 1 second. We'll get to that. That's after this, all right? Before we get to that, though, again, if you reduce the area, there's less water in a sense coming out, but the water's coming out faster. So you would still get the same amount of volume in a given time period. Okay? So again, it makes no sense to cover up the end of a garden hose to try and make the water come out faster, because it doesn't actually. It comes out at a higher velocity, but there's less water coming out. Okay? So you still fill up a pool, or not a pool really, a bucket in the same given amount of time. Okay?
That's really the amount of lights over time.
Say again?
That's kind of like work, the amount of work over time. The amount of
Not work over time, it's volume over time. Yeah, volume over time. All right, so to follow up with the question that Stash just asked, let's talk about pressure and how it changes internally. Okay? So let's say we've got a scenario where we've got, in class we did it from a large area to a small area. So I'm going to write it backwards this time. So maybe this will help open up some ideas. So imagine water flowing through a pipe, and then it continues through a much bigger cross section. So there's water coming through the pipe, and then it continues through a much bigger cross section. Is the water speed faster or slower in the beginning? In the beginning. Why? Smaller area. So I'm going to say V1, I'm going to say V2. I'm going to say V1 is greater than V2, clearly. So what has happened to the water? Has it sped up or slowed down when it makes this transition?
Slow down.
It slowed down. So the acceleration is
Less.
Negative.
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 Don't say less, it's negative. For velocity to decrease, the acceleration must be negative. So, because of this, we say that the acceleration is negative If acceleration is negative from F equals ma, the net force must also be negative.
Yes.
Okay? If the net force is negative, we also have a net negative pressure. So that's the reason it's going to change the pressure behind that. Does that make sense?
If you're holding like a hose and then don't you feel a lot of pressure on your thumb? Is that because it's still in the larger intensity?
Yeah, let me answer that question. That's a good question. So here's the question. If you put your thumb over the hose, it feels like there's a lot of pressure on your thumb. And there is. But the pressure you're feeling is from behind it. The pressure at the nozzle at the release is less. That's the only way it would work. It's like, here's a good example for you. You go to a Shake Shack and you get a shake, right? And imagine you're drinking the shake. The way it works is a differential in pressure. When you actually sip through a straw, you're changing the pressure. And that pressure is using like a capillary effect and pulling that fluid up the straw. So it's a difference in pressure that is attracting the fluid, really, or moving the fluid. Okay? Good question. Very good. Jeff? Like you give blood with those too, yeah. Those little capillary tubes.
Oh yeah, like with like a shot. You can suck it in. Okay, it's not supposed to.
Good.
Oh wait, what does it have to do when remember nothing changes when you do it? It was like counterintuitive, where it was like nothing changes when you would think that the pressure would increase when it's in a larger area.
That's what we were just saying, exactly.
No, but you said it actually did. Oh yeah. Oh, the pressure. Okay, so the pressure does increase when it's in a larger area. It's always constant.
No. Remember the example we did the other day when we talked about a hose and you put your thumb over it? What happens is the pressure is higher behind your finger and lower at the nozzle. This example is the opposite of that. Okay? It'd be lower pressure here and higher pressure over here.
That's what's counterintuitive.
Yes.
In a larger area, it's higher pressure.
Yes, it's very counterintuitive. One would think it'd be low pressure by looking at, like, thinking, okay, there's more room to flow. But looking at velocities and forces, we can see that it's actually counterintuitive. Okay? All right. The term pressure. What is pressure a function? Pressure equals what?
Area over something over area.
There it is. So, what was the example I gave in class? Who remembers? What did I talk about? How could you simply talk about pressure? Mechanical advantage we talked about there. A little different. We're going to use pressure in Pascal's principle, but that's not what I was talking about. What was the example I did in front of the room? I said if you stand on 2 feet, what happens when? Yeah, it's the area. Again, the area. So, you take your mass, or your weight in this case, say it's 160 pounds, 50 pounds, 170 pounds, whatever it is. And you have that much force acting over an area of 2 feet. Whatever, not feet as in units, but my feet on the ground.
Yeah.
If I lift one of my feet, now it's acting over how much area? Half of it. 1 foot, yes. Half of the area. So the pressure goes up a lot because you're halving the area. So the pressure, so you're decreasing the denominator, so it increases the result always. Okay? So more pressure, and think logically. Isn't it tougher to stand on 1 foot?
Yeah.
Because of the pressure on your foot. That's why. Okay? Alright, we've talked about this term, and I want someone to describe it and maybe define it as well. There's a term we use called apparent weight. Apparent weight. How can you describe apparent weight? And what I want you to do is use the word force in your description of apparent weight. How would you make a statement describing apparent weight using the word force? Somebody else. I appreciate it. I do. Thank you. Mash, go ahead.
The net force on the object.
It's the overall net force on the object, okay? But what is the net force defined as? What's the equation for net force on an object? In this case, underwater. If I drew a free body diagram, what's pulling the object down into the water? Okay, and what's pushing back up?
What?
What's pushing back up on it?
Oh,
Okay, but it's in water, so we don't call it normal force. What do we call it? The buoyant force. So, the apparent weight is exactly what Masha said. It's F net. That's what it is. So, for example, if you're not standing in water, what's the buoyant force? If you're not in water. It's 0. So your apparent weight is your weight.
No.
Guys, stop. The noises are annoying. The apparent weight is the weight. Okay? But, that's different. Hold on. But if you're in water, what happens to your actual weight? Paul. Paul. No, thank you. Come move. You feel lighter. You feel lighter. The reason you feel lighter is because FB has a value now. And instead of FG being your weight, it's FB minus FG now. That's what you actually feel. So imagine you weigh 200 newtons. Put a 200 in here. Okay? If you're not in water, the buoyant force is 0, so you weigh 200. But if you're in water, for example, and let's say hypothetically the buoyant force is 140 newtons, how much do you feel like you weigh?
0.
No, 20 or 60, sorry.
60.
I thought it was, you felt like it was nothing.
60. That's when you're floating.
Oh.
Again, guys, only when you're floating is FB equal to FG. Okay? So yeah, your weight is 60 newtons downward, which is negative 60. That's why the negative sign is there, okay? Keep that in mind. Okay? Again, if you're floating, it's 200 minus 200, which is, that's why you feel like you're weightless when you're floating. Okay? All right. All right, we talked about the pressure on an object underwater, and we defined it with an equation. And if you remember, the equation was the following. P equals P0 plus rho GH. Let's talk about some terms that we didn't really clearly, I don't think, define in class too well. This here is called the absolute pressure. I don't think I actually use these words, and I want to make sure we're clear with them. And I'll explain why they're called the things they're called. This is called the atmospheric pressure, which I did talk about. That's the amount of air weighing down on you. And this part is the water pressure on top of you. Okay? Just to reiterate, the pressure you feel when you're underwater is not just the water, but the air and the atmosphere on top of the water itself. So it is the sum of these two quantities. Now, if you keep going deeper and deeper and deeper into the water, in the ocean, what's going to happen to your pressure? Yeah, because H goes up, doesn't it? As you go deeper, H goes up. The depth goes up. So what's happening is this. If you go down completely to the bottom, what will happen to an object eventually? What will happen to it? It'll crush on itself. Okay, it'll implode. So if you had like a can of soda, and it's somebody literally in the ocean that was able to sink down, it would completely go. Okay, the pressure would be too much on it, and it would collapse. Any can. Your body would. You cannot send down like a submarine down the ocean. There's parts of the ocean that are there's too much pressure that anything we know can't get down there. So we can hypothesize what was down there based on sending rays of light and sonar and looking at the shape of the floor using sonar waves. But we can't actually see what's happening.
I think that says something about that we should not go down there.
Yeah, right? If you can't see what's down there, leave it alone. Like leave it alone down there. Fernando, be nice. Okay? Alright. That's the conceptual stuff. Let's talk about some mathematical now. Some mathematical. I'll give you some hints as to what you can expect. We're not going to go through them, obviously, but I'll give you some hints. Let's see. Okay, remember the example we did with the lead ball bearing sitting on top of mercury and it floated, and we had the lead ball bearing that was sitting on top of mercury and it was floating and stuff, and you had to calculate all those things like the weight of the ball bearing using rho VG. So remember this first. Remember this. Mass of the object times gravity, but mass, as Jeff said, is really rho V. So we can always use this for the force of gravity. This is not given on the test. This formula is not given. mg is given. You need to know to replace m with rho v. Because this is given on the test, actually. This formula is given. So if you solve for m, you can simply replace it. So you need to be able to find the weight of an object even if you're not given the mass. That's one part for sure. You need to be able to determine if an object is sinking or floating based on like calculating either the buoyant force or knowing if the densities are bigger or smaller. What was the formula for buoyant force? And this is given. What is the formula for buoyant force? Jeff? But in general though, not relating to Fg. That's if it's floating, it is, yeah. But what's the actual formula for buoyant force?
Oh, FV equals density times velocity,
Volume.
times G.
But what is the difference in these two formulas? What does the F stand for?
Fluid.
Yeah, so the density of the fluid, the volume of the fluid displaced, times G. The density of the object times the volume of the object times G. They're different. The subscripts are very important here. And they're not final and initial. It's object and fluid. Make sure you're able to calculate the apparent weight of an object that's submerged. Or maybe on the top of a surface. If it's on top of the surface, what's the apparent weight? Zero. So that's easy. But if it's not, remember this formula. Also not given. You need to come up with this formula just by simply looking at a free body diagram. Okay, there's your free body diagram. Based on that diagram, you can always come up with this equation. It's not given to you. Okay, you're not given that last equation there.
Wait, sorry, just so one question, we find the apparent weight, and you said, and most likely, you can use this, doesn't matter, but when it's submerged,
It has an apparent weight. You have to find that using the calculation from FV and the calculation from FG. You're going to use volume up here, Joe. So you can plug these expressions right in. So you can do this, right? That was kind of stupid to write it that way, but... Sorry. Okay?
Is our,
I know I drew the arrows backwards, but... Again, guys, you can plug in those expressions for Fg and Fb into that formula to make it easier. Now, if the object is submerged, aren't Vf and Vo the same?
no, that's only
If it's submerged. If it's submerged. So what could you do? If an object is submerged, and we did this in class.
and you can substitute, right?
If an object is submerged, when we plug in here,
Cancel out the
not cancel, be careful with that word. A lot of you use it. You're not canceling. You're factoring it out.
Oh,
Okay.
yeah, that's more about PF in parentheses times the quantity, density F minus density O.
Yep, that's exactly right.
I mean, yeah, Vg times quantity, PF.
Okay, this last line I just wrote only works if the object is submerged. This last line here, because when it's submerged, the VF and the VO are the same. So you can drop these subscripts here, cross them off, and then you can factor out V and you can factor out G. This only works when an object is submerged. Okay, second math part. We talked yesterday about an example of pressure where there was a car and there were 4 tires. Okay? Do you remember that example where there were 4 tires? Yes? No? Maybe?
Yeah.
Okay? We did it yesterday in class. You should be able to do something as difficult as that for sure. Okay, so expect something like that.
Big car, wheels.
Yeah.
Find it. Which one was it?
We did it yesterday. I don't know the rules. Pascal's principle. Let's talk about Pascal's principle. What does it say? What is Pascal's principle? Not P equals F over A, Stash.
It's the area times the pressure. It's like it's I forget what the variables are, but it's the before if it's.
What does it say though? I'm not asking for the formula. What does it say? Guys, what does Pascal's principle say? You're not answering that question. I'm not asking for like equations or stuff. What is Pascal's principle? If we don't know it, we should really start thinking about studying that for sure.
Pressure is conserved.
The pressure is conserved in a closed container. It's equal throughout. And what that says then as a result is this.
You mean on the different sides?
Okay, on all the sides or all the walls, which allowed us to use the formula you were trying to get at. Okay, which is this. Okay, again, you're not given this formula on the test because this comes from a principle. So when you have a problem with a hydraulic lift, remember, with the car and the lift on the other side, this is the formula you're going to use because it's an internal pressure that is conserved. Did anybody try the egg thing? Did anyone actually try it? Remember I told you guys about the egg? Did you make a mess, really? It broke? Did you actually try it or not? Did it work at first and then it broke? Did it work at all for you? If you use your fingertips and don't do it evenly, it's going to break. But the idea is that you have to put equal pressure on it. It didn't break, okay, yeah. You got to be careful when you're squeezing it, or else if you do it at an angle, it's not going to work. All right. You need to be able to do a mathematical problem using this formula with a hydraulic lift and with two different areas of the pistons. Okay? You need to know your mathematical formulas for area. If you're given radius and you need to find the area in a formula, you need to use pi r squared here and here. If you're given a diameter, you have to use pi. Good. Quantity d over 2 squared. Okay? Again, these are area expressions. If you're given them, you need to substitute them into that formula. Same thing with the continuity equation. You have to substitute in there. With that said, you need to do an example with the continuity equation. AV equals AV. Calculating some missing variable. Okay, that's definitely one of the math problems. And the last math problem you'll have has to do with the pressure underwater, the absolute pressure. So being able to use this formula mathematically. Maybe solving for the depth or the density of the fluid, or maybe solving for the actual pressure on the fluid. P0 and G are given, they're constants. So you're never going to be asked to solve for P0 or G unless I say, find the atmospheric pressure, P0, on Mars. If the pressure underwater is this and this and this, then you have to solve for P0. Okay? But on Earth, P0 is a constant.
And on Earth.
Subtracting, yep.
And you would ask, like, the object is similar to the water, what is the pressure?
Yeah, exactly. At a certain depth, with this fluid, with this density, what is the pressure?
And to solve that, you just subtract A.
Yep. Whatever the numbers are.
Does that negative distribute to that entire, too much number?
It's a negative to whatever this whole quantity is as an entity. That's only when you're adding, Jeff, you distribute the negative. The test is Tuesday. When you have a negative sign and this is a parentheses for the sum, when you add it, it's a distributive.
Let's say there's a negative sign. The negative sign.
You only distribute a negative sign when it's a distributive property. When there's a quantity, then there's a sum inside of it. One sec, Maj. If you have any questions with density, they will be given on the test. Everybody hear me?
Yeah.
Okay, if there's any problem with density, it will be given on the test, the density value. Either in the table form, or I'll give you the density right in the problem. You should know water by now, it's 1,000, but I'll give it to you anyway if it's on there, just so you're prepared. Masha. What number is P0? 1 times 10 to the 5th pascals. And that is called 1 atmosphere. And we call it an atmosphere, meaning it's the atmosphere pressure on Earth. Okay? This is given, guys. That's given at the bottom.
I know that ATM is also involved with temperature. Let's say you give us something else different. You're not going to give us something.
We didn't even go into temperature. No. Okay? All right, guys? Yes? Yes?
Yeah.
All right, cool. We got a few minutes extra right now.